The Large Hadron Collider, or LHC, is the world's largest and highest energy particle accelerator. It was built by the European Organization for Nuclear Research, known as CERN, between 1998 and 2008, in collaboration with over 10,000 scientists and hundreds of universities and laboratories across more than 40 countries. It lies in a tunnel 27 kilometers, or 17 miles, in circumference, and as deep as 175 meters, or 574 feet, beneath the France. Switzerland border near Geneva. The first collisions were achieved in 2010 at an energy of 3.5 teraelectron-volts per beam, about 4 times the previous world record. The discovery of the Higgs boson at the LHC was announced in 2012. Between 2013 and 2015, the LHC was shut down and upgraded. After those upgrades, it reached 6.5 TeV per beam, giving 13.0 TeV total collision energy. At the end of 2018, it was shut down for maintenance and further upgrades, and reopened over 3 years later in April 2022. The collider has 4 crossing points, where the accelerated particles collide. 9 detectors, each designed to detect different phenomena, are positioned around the crossing points. The LHC primarily collides proton beams, but it can also accelerate beams of heavy ions, such as in lead-lead collisions and proton-lead collisions. The LHC's goal is to allow physicists to test the predictions of different theories of particle physics, including measuring the properties of the Higgs boson, searching for the large family of new particles predicted by supersymmetric theories, and studying other unresolved questions in particle physics. The term hadron refers to subatomic composite particles, composed of quarks held together by the strong force, analogous to the way that atoms and molecules are held together by the electromagnetic force. The best-known hadrons are the baryons such as protons and neutrons. Hadrons also include mesons such as the pion and kaon, which were discovered during cosmic ray experiments in the late 1940s and early 1950s. A collider is a type of particle accelerator that brings 2 opposing particle beams together such that the particles collide. In particle physics, colliders, though harder to construct, are a powerful research tool because they reach a much higher center of mass energy than fixed target setups. Analysis of the byproducts of these collisions gives scientists good evidence of the structure of the subatomic world and the laws of nature governing it. Many of these byproducts are produced only by high-energy collisions, and they decay after very short periods of time. Thus, many of them are hard or nearly impossible to study in other ways. Many physicists hope that the Large Hadron Collider will help answer some of the fundamental open questions in physics, which concern the basic laws governing the interactions and forces among elementary particles and the deep structure of space and time, particularly the interrelation between quantum mechanics and general relativity. These high-energy particle experiments can provide data to support different scientific models. For example, the Standard Model and Higgsless Model required high-energy particle experiment data to validate their predictions and allow further theoretical development. The Standard Model was completed by detection of the Higgs boson by the LHC in 2012. LHC collisions have explored other questions as well. The collider is contained in a circular tunnel with a circumference of 26.7 kilometers or 6.6 miles, at a depth ranging from 50 to 105 meters, or 100 round. The variation in depth was deliberate to reduce the amount of tunnel that lies under the Jura Mountains to avoid having to excavate a vertical access shaft there. A tunnel was chosen to avoid having to purchase expensive land on the surface and to take advantage of the shielding against background radiation that the Earth's crust provides. The 3.8-meter or 12-foot wide concrete-lined tunnel constructed between 1983 and 1988 was formerly used to house the Large Electron-Positron Collider. The tunnel crosses the border between Switzerland and France at 4 points, with most of it in France. Surface buildings hold ancillary equipment such as compressors, ventilation equipment, control electronics, and refrigeration plants. The collider tunnel contains two adjacent parallel beam lines, or beam pipes, each containing a beam, which travel in opposite directions around the ring. The beams intersect at 4 points around the ring, which is where the particle collisions take place. Some 1022 dipole magnets keep the beams on their circular path, while an additional 392 quadrupole magnets are used to keep the beams focused, with stronger quadrupole magnets close to the intersection points, in order to maximize the chances of interaction where the two beams cross. Magnets of higher multipole orders are used to correct smaller imperfections in the field geometry. In total, about 10,000 superconducting magnets are installed, with each of the 1232 dipole magnets having a mass of 27 tons. About 96 tons of superfluid helium-4 is needed to keep the magnets, made of copper-clad niobium titanium, at their operating temperature of 1.9 Kelvin, or minus 271.25 degrees Celsius, making the LHC the largest cryogenic facility in the world at liquid helium temperature. The LHC uses 1,200 tons of niobium titanium superconductor. During LHC operations, the CERN site draws roughly 200 megawatts of electrical power from the French electrical grid, which, for comparison, is about one-third the energy consumption of the city of Geneva. The LHC accelerator and detectors draw about 120 megawatts of that. Each day of its operation generates 15 petabytes of data. When running at an energy of 6.5 tera-electronvolts per proton, once or twice a day, as the protons are accelerated from 450 giga-electronvolts to 6.5 tera-electronvolts, the field of the superconducting dipole magnets is increased from 0.54 to 7.7 teslas. The protons each have an energy of 6.5 tera-electronvolts, giving a total collision energy of 13 tera-electronvolts. At this energy, the protons have a Lorentz factor of about 6,930 and move at about 0.999999 times the speed of light, or about 3.1 meters per second, or 11 kilometers per hour, slower than the speed of light. It takes less than 90 microseconds for a proton to travel 26.7 kilometers around the main ring. This results in 11,024.5 revolutions per second for protons, whether the particles are at low or high energy in the main ring, since the speed difference between these energies is beyond the fifth decimal. Rather than having continuous beams, the protons are bunched together into up to 2,808 bunches, with 100 billion protons in each bunch, so that interactions between the two beams take place at discrete intervals, mainly 25 nanoseconds apart, providing a bunch collision rate of 40 megahertz. It was operated with fewer bunches in the first years. The design luminosity of the LHC is 10 to the 34th power per centimeter squared per second, which was first reached in June 2016. By 2007, twice this value was achieved. Before being injected into the main accelerator, the particles are prepared by a series of systems that successively increase their energy. The first system is the linear particle accelerator, LINAC-4, generating 160 mega-electronvolts, negative hydrogen ions, which feeds the proton synchrotron booster. There, both electrons are stripped from the hydrogen ions, leaving only the nucleus containing one proton. Protons are then accelerated to 1.4 giga-electronvolts and injected into the proton synchrotron, where they are accelerated to 25 giga-electronvolts. Finally, the superproton synchrotron is used to increase their energy further to 450 giga-electronvolts before they are at last injected, over a period of several minutes, into the main ring. Here, the proton bunches are accumulated, accelerated over a period of 20 minutes to their peak energy, and finally circulated for 10 to 24 hours, while collisions occur at the 4 intersection points. The LHC physics program is mainly based on proton-proton collisions. However, during shorter running periods, typically 1 month per year, heavy ion collisions are included in the program. While lighter ions are considered as well, the baseline scheme deals with lead ions. The lead ions are first accelerated by the linear accelerator LINAC-3, and the low-energy ion ring is used as an ion storage and cooler unit. The ions are then further accelerated by the PS and SPS before being injected into LHC ring, where they reach an energy of 2.3 tera-electron-volts per nucleon, or 574 tera-electron-volts per ion, higher than the energies reached by the relativistic heavy ion collider. The aim of the heavy ion program is to investigate quark-gluon plasma, which existed in the early universe. 9 detectors have been built in large caverns excavated at the LHC's intersection points. 2 of them, the ATLAS experiment and the Compact Muon Solenoid, or CMS, are large general-purpose particle detectors. ALICE and LHCb have more specialized roles, while the other 5, Totem, Moedl, LHCf, SND, and Phaser, are much smaller and are for very specialized research. The ATLAS and CMS experiments discovered the Higgs boson, which is strong evidence that the Standard Model has the correct mechanism of giving mass to elementary particles. Data produced by LHC, as well as LHC-related simulation, were estimated at 15 petabytes per year. The LHC computing grid was constructed as part of the LHC design to handle the large amounts of data expected for its collisions. It is an international collaborative project that consists of a grid-based computer network infrastructure initially connecting 140 computing centers in 35 countries, over 170 centers in more than 40 countries as of 2012. It was designed by CERN to handle the significant volume of data produced by LHC experiments, incorporating both private fiber optic cable links and existing high-speed portions of the public internet, to enable data transfer from CERN to academic institutions around the world. The LHC computing grid consists of 4 global federations across Europe, Asia-Pacific, and the Americas. The Distributed Computing Project, LHC Home, was started to support the construction and calibration of the LHC. The project uses the Buoyancy platform, enabling anybody with an internet connection and a computer running Mac OS X, Windows, or Linux to use their computer's idle time to simulate how particles will travel in the beam pipes. With this information, the scientists are able to determine how the magnet should be calibrated to gain the most stable orbit of the beams in the ring. In August 2011, a second application called Test for Theory went live, which performs simulations against which to compare actual test data to determine confidence levels of the results. By 2012, data from over 6 quadrillion, or 6 times 10 to the 15th power, LHC proton-proton collisions had been analyzed. The LHC computing grid had become the world's largest computing grid in 2012, comprising over 170 computing facilities in a worldwide network across more than 40 countries. The LHC first went operational on September 10, 2008, but initial testing was delayed for 14 months from September 2008 to November 2009, following a magnet quench incident that caused extensive damage to over 50 superconducting magnets, their mountings, and the vacuum pipe. During its first run from 2010 to 2013, the LHC collided 2 opposing particle beams of either protons at up to 4 tera-electron-volts, or 4 tera-electron-volts, or 64 microjoules, or lead nuclei at 74 tera-electron-volts per nucleus, or 2.786 tera-electron-volts per nucleon. Its first-run discoveries included the long-sought Higgs boson, several composite particles called hadrons, like the key B3p bottomonium state, the first creation of a quark-gluon plasma, and the first observations of the very rare decay of the B's meson into 2 muons, which challenged the validity of existing models of supersymmetry. The size of the LHC constitutes an exceptional engineering challenge with unique operational issues on account of the amount of energy stored in the magnets and the beams. While operating, the total energy stored in the magnets is 10 gigajoules, equivalent to 2,400 kilograms of TNT, and the total energy carried by the 2 beams reaches 724 megajoules, equivalent to 73 kilograms of TNT. Loss of only 1/10,000th part of the beam is sufficient to quench a superconducting magnet, while each of the 2 beam dumps must absorb 362 megajoules, equivalent to 87 kilograms of TNT. These energies are carried by very little matter, under nominal operating conditions with 2,808 bunches per beam, 1.5 times 10 to the 11th power. Protons per bunch, the beam pipes contain 1.0 times 10 to the minus 9th. Power grams of hydrogen, which, in standard conditions for temperature and pressure, would fill the volume of 1 grain of fine sand. With a budget of 7.5 billion euros, about 9 billion US dollars as of January 2010, for the accelerator and 1.16 billion Swiss francs, about 1.1 billion US dollars, for the detector systems, the LHC is one of the most expensive scientific instruments ever built. CERN has developed a proposal for the future circular collider, a 100-kilometer tunnel, with a projected cost ranging from 15 billion to 21 billion euros. It would use the LHC ring as pre-accelerator, similar to how the LHC uses the smaller superproton synchrotron. It is CERN's opening bid in a priority-setting process called the European Strategy for Particle Physics Update, and will affect the field's future well into the second half of the century. As of 2023, no fixed plan exists, and it is unknown if the construction will be funded. The safety of high-energy particle collisions was a topic of widespread discussion and interest during the time when the relativistic heavy ion collider and later the Large Hadron Collider were being constructed and commissioned. Concerns arose that such high-energy experiments designed to produce novel particles and forms of matter had the potential to create harmful states of matter or even doomsday scenarios. Claims escalated as commissioning of the LHC drew closer, around 2008 to 2010. The claimed dangers included the production of stable micro-black holes and the creation of hypothetical particles called strangelets. And these questions were explored in the media, on the internet, and at times through the courts. To address these concerns in the context of the LHC, CERN mandated a group of independent scientists to review these scenarios. In a report issued in 2003, they concluded that, like current particle experiments such as the RHIC, the LHC particle collisions pose no conceivable threat. A second review of the evidence commissioned by CERN was released in 2008. The report, prepared by a group of physicists affiliated to CERN but not involved in the LHC experiments, reaffirmed the safety of the LHC collisions in light of further research conducted since the 2003 assessment. It was reviewed and endorsed by a CERN committee of external scientists and by the Executive Committee of the Division of Particles and Fields of the American Physical Society, and was later published in the peer-reviewed Journal of Physics G by the United Kingdom Institute of Physics, which also endorsed its conclusions. The report ruled out any doomsday scenario at the LHC, noting that the physical conditions and collision events which exist in the LHC, RHIC, and other experiments occur naturally and routinely in the universe without hazardous consequences, including ultra-high energy cosmic rays observed to impact Earth with energies far higher than those in any man-made collider. Particle colliders are a type of particle accelerator used by physicists as a research tool to understand fundamental aspects of the universe. Their operation involves directed beams of particles accelerated to very high kinetic energy and allowed to collide. Analysis of the byproducts of these collisions gives scientists good evidence of the structure of the subatomic world and the laws of nature governing it. These may become apparent only at high energies and for tiny periods of time, and therefore may be hard or impossible to study in other ways. Because of the high energy levels involved, concerns have arisen at times in the public arena as to whether such collisions are safe, or whether they might, by reason of their extreme energy, trigger unforeseen problems or consequences. Concerns were noted during the construction of the Large Hadron Collider, which began operations in 2008, is the world's largest and highest energy particle accelerator complex, intended to collide opposing beams of either protons or lead nuclei with very high kinetic energy. It was built by the European Organization for Nuclear Research near Geneva in Switzerland. The LHC's main purpose is to explore the validity and limitations of the Standard Model, the current theoretical picture for particle physics. The first particle collisions at the LHC, took place shortly after startup in November 2009 at energies up to 1.2 tera-electron-volts per beam. On March 30, 2010, the first planned collisions took place between two 3.5 tera-electron-volt beams, which set another new world record for the highest energy man-made particle collisions. In 2012, the beam energy was increased to 4 tera-electron-volts. After upgrades in 2013 and 2014, collisions in 2015 and 2006 happened at an energy of 6.5 tera-electron-volts per proton. Similar concerns had previously also been raised in the context of the relativistic heavy ion collider, with Frank Close, professor of physics at the University of Oxford, commenting at the time that the chance of strangelet creation is like you winning the major prize on the lottery 3 weeks in succession. The problem is that people believe it is possible to win the lottery 3 weeks in succession. Concerns about possible adverse consequences were raised in connection with the RHIC particle accelerator. After detailed studies, scientists reached such conclusions as, beyond reasonable doubt, heavy ion experiments at RHIC will not endanger our planet, and that there is powerful empirical evidence against the possibility of dangerous strangelet production. Before the relativistic heavy ion collider started operation, critics postulated that the extremely high energy could produce catastrophic scenarios, such as creating a black hole, a transition into a different quantum mechanical vacuum, Seafall's vacuum, or the creation of strange matter that is more stable than ordinary matter. These hypotheses are complex, but many predict that the Earth will be destroyed in a time frame from seconds to millennia, depending on the theory considered. However, the fact that objects of the solar system, such as the Moon, have been bombarded with cosmic particles of significantly higher energies than that of RHIC and other man-made colliders for billions of years, without any harm to the solar system, were among the most striking arguments that these hypotheses were unfounded. The other main controversial issue was a demand by critics for physicists to reasonably exclude the probability for such a catastrophic scenario. Physicists are unable to demonstrate experimental and astrophysical constraints of zero probability of catastrophic events, nor that tomorrow Earth will be struck with a doomsday cosmic ray. They can only calculate an upper limit for the likelihood. The result would be the same destructive scenarios described above, although obviously not caused by humans. According to this argument of upper limits, RHIC would still modify the chance for the Earth's survival by an infinitesimal amount. Concerns were raised in connection with the RHIC particle accelerator, both in the media and in the popular science media. The risk of a doomsday scenario was indicated by Martin Rees, with respect to the RHIC, as being at least a 1 in 50 million chance. With regards to the production of strangelets, Frank Close, professor of physics at the University of Oxford, indicates that the chance of this happening is like you winning the major prize in the lottery 3 weeks in succession. The problem is that people believe it is possible to win the lottery 3 weeks in succession. After detailed studies, scientists reached such conclusions as, beyond reasonable doubt, heavy ion experiments at RHIC will not endanger our planet, and that there is powerful empirical evidence against the possibility of dangerous strangelet production. The debate started in 1999 with an exchange of letters in Scientific American between Walter L. Wagner and F. Wilczek in response to a previous article by M. Mukherjee. The media attention unfolded with an article in UK, Sunday Times of July 18, 1999, by J. Leake, closely followed by articles in the US media. The controversy mostly ended with the report of a committee convened by the director of Brookhaven National Laboratory, J. H. Marburger, ostensibly ruling out the catastrophic scenarios depicted. However, the report left open the possibility that relativistic cosmic ray impact products might behave differently while transiting Earth compared to at-rest, RHIC products, and the possibility that the qualitative difference between high-energy proton collisions with Earth or the Moon might be different than on-gold collisions at the RHIC. Wagner tried subsequently to stop full-energy collision at RHIC by filing federal lawsuits in San Francisco and New York City, but without success. The New York suit was dismissed on the technicality that the San Francisco suit was the preferred forum. The San Francisco suit was dismissed, but with leave to refile if additional information was developed and presented to the court. On March 17, 2005, the BBC published an article implying that researcher Horatiu Nastase believes black holes have been created at RHIC. However, the original papers of H. Nastase and the New Scientist article cited by the BBC state that the correspondence of the hot dense QCD matter created in RHIC to a black hole is only in the sense of a correspondence of QCD scattering in Minkowski space and scattering in the ADS5 Nicex5 space in ADSX CFT. In other words, it is similar mathematically. Therefore, RHIC collisions might be described by mathematics relevant to theories of quantum gravity within ADSX CFT, but the described physical phenomena are not the same. In the run-up to the commissioning of the LHC, Walter L. Wagner, an original opponent of the RHIC, Luis Sancho, a Spanish science writer, and Otto Ressler, a German biochemist, expressed concerns over the safety of the LHC and attempted to halt the beginning of the experiments through petitions to the United States and European courts. These opponents assert that the LHC experiments have the potential to create low-velocity micro-black holes that could grow in mass or release dangerous radiation leading to doomsday scenarios, such as the destruction of the Earth. Other claimed potential risks include the creation of theoretical particles called strangelets, magnetic monopoles, and vacuum bubbles. Based on such safety concerns, United States federal judge Richard Posner, Future of Humanity Institute research associate, Toby Ord, and others have argued that the LHC experiments are too risky to undertake. In the book, Our Final Century, Will the Human Race Survive the 21st Century? English cosmologist and astrophysicist Martin Rees had calculated an upper limit of 1 in 50 million for the probability that RHIC will produce a global catastrophe or black hole. However, Rees has also reported not to be losing sleep over the collider and trusts the scientists who have built it. He has stated, "My book has been misquoted in 1 or 2 places. I would refer you to the up-to-date safety study." The risk assessments of catastrophic scenarios at the LHC sparked public fears, and some scientists associated with the project received protests. The Large Hadron Collider team revealed that they had received death threats and threatening emails and phone calls demanding the experiment be halted. On September 1, 2008, Romania's Conservative Party held a protest before the European Commission mission to Bucharest, demanding that the experiment be halted because it feared that the LHC could create dangerous black holes. Various widely circulated newspapers have reported doomsday fears in connection with the collider, including The Times, The Guardian, The Independent, The Sydney Morning Herald, and Time. Among other media sources, CNN mentioned that some have expressed fears that the project could lead to the Earth's demise, but it assured its readers with comments from scientists like John Huth, who said that it was baloney. MSNBC said that there are more serious things to worry about, and allayed fears that the atom smasher might set off earthquakes or other dangerous rumblings. The results of an online survey it conducted indicate that a lot of the public know enough not to panic. The BBC stated, "The scientific consensus appears to be on the side of CERN's theorists, who say the LHC poses no conceivable danger." Brian Greene in the New York Times reassured readers by saying, "If a black hole is produced under Geneva, might it swallow Switzerland and continue on a ravenous rampage until the Earth is devoured? It's a reasonable question with a definite answer, no." On September 11, 2008, a 16-year-old girl from Sarangpur, Madhya Pradesh, India, committed suicide, having become distressed about predictions of an impending doomsday made on an Indian news channel covering the LHC. After the dismissal of the federal lawsuit, The Daily Show's correspondent John Oliver interviewed Walter L. Wagner, who declared that he believed the chance of the LHC destroying the Earth to be 50%, since it will either happen or it won't. Although the standard model of particle physics predicts that LHC energies are far too low to create black holes, Some extensions of the Standard Model posit the existence of extraspatial dimensions, in which it would be possible to create micro-black holes at the LHC at a rate of the order of 1 per second. According to the standard calculations, these are harmless because they would quickly decay by Hawking radiation. Hawking radiation is a thermal radiation predicted to be emitted by black holes due to quantum effects. Because Hawking radiation allows black holes to lose mass, black holes that lose more matter than they gain through other means are expected to dissipate, shrink, and ultimately vanish. Smaller micro-black holes, which could be produced at the LHC, are currently predicted by theory to be larger net emitters of radiation than larger black holes, and to shrink and dissipate instantly. The LHC Safety Assessment Group indicates that there is broad consensus among physicists on the reality of Hawking radiation, but so far no experiment has had the sensitivity required to find direct evidence for it. According to the LSAG, even if micro-black holes were produced by the LHC and were stable, they would be unable to accrete matter in a manner dangerous for the Earth. They would also have been produced by cosmic rays, and have stopped in neutron stars and white dwarfs. And the stability of these astronomical bodies means that they cannot be dangerous. Stable black holes could be either electrically charged or neutral. If stable microscopic black holes had no electric charge, their interactions with the Earth would be very weak. Those produced by cosmic rays would pass harmlessly through the Earth into space, whereas those produced by the LHC could remain on Earth. However, there are much larger and denser astronomical bodies than the Earth in the universe. Black holes produced in cosmic ray collisions with bodies such as neutron stars and white dwarf stars would be brought to rest. The continued existence of such dense bodies, as well as the Earth, rules out the possibility of the LHC producing any dangerous black holes. Strangelets are small fragments of strange matter, a hypothetical form of quark matter that contain roughly equal numbers of up, down, and strange quarks, and that are more stable than ordinary nuclei. Strangelets would range in size from a few femtometers to a few meters across. If strangelets can actually exist, and if they were produced at the LHC, they could conceivably initiate a runaway fusion process in which all the nuclei in the planet would be converted to strange matter, similar to a strange star. The probability of the creation of strangelets decreases at higher energies. As the LHC operates at higher energies than the RHIC or the heavy ion programs of the 1980s and 1990s, the LHC is less likely to produce strangelets than its predecessors. Furthermore, models indicate that strangelets are only stable or long-lived at low temperatures. Strangelets are bound at low energies, in the range of 1 to 10 megaelectronvolts, while the collisions in the LHC release energies in the range of 7 to 14 teraelectronvolts. Thermodynamics very strongly disfavors the formation of a cold condensate that is an order of magnitude cooler than the surrounding medium. As an example, it is about as likely as producing an ice cube in a furnace. Otto Rüssler, a German chemistry professor at the University of Tübingen, argues that micro-black holes created in the LHC could grow exponentially. On July 18, 2008, Rüssler met with a CERN physicist, Rolf Landau, with whom he discussed his safety concerns. Following the meeting, Landau asked another expert, Hermann Nicolai, director of the Albert Einstein Institute in Germany, to examine Rüssler's arguments. Nicolai reviewed Otto Rüssler's research paper on the safety of the LHC and issued a statement highlighting logical inconsistencies and physical misunderstandings in Rüssler's arguments. Nicolai concluded that this text would not pass the referee process in a serious journal. Domenico Giulini also commented with Hermann Nicolai on Otto Rüssler's thesis, concluding that his argument concerns only the general theory of relativity and makes no logical connection to LHC physics. The argument is not valid. The argument is not self-consistent. On August 22, 2008, a group of German physicists, the Committee for Elementary Particle Physics, published an open letter further dismissing Rüssler's concerns and carrying assurances that the LHC is safe. Otto Rüssler was due to meet Swiss President Pascal Couchepin in August 2008 to discuss this concern, but it was later reported that the meeting had been canceled, as it was believed Rössler and his fellow opponents would have used the meeting for their own publicity. On August 27, 2008, Rainer Plege, a German astrophysicist, posted a research paper on the RxIve web archive concluding that LHC safety studies have not definitely ruled out the potential catastrophic threat from microscopic black holes, including the possible danger from Hawking radiation emitted by black holes. In a follow-up paper posted on the RxIve on August 28, 2008, Stephen Giddings and Michelangelo Mangano responded to Plege's concerns. They pointed out what they see as a basic inconsistency in Plege's calculation and argued that their own conclusions on the safety of the collider, as referred to in the LHC Safety Assessment Report, remain robust. Giddings and Mangano also referred to the research paper Exclusion of Black Hole Disaster Scenarios at the LHC, which relies on a number of new arguments to conclude that there is no risk due to many black holes at the LHC. On January 26, 2009, Roberto Casadio, Sergio Fabi, and Benjamin Harms posted on the RxIve a paper, later published on Physical Review D, ruling out the catastrophic growth of black holes in the scenario considered by Plege. In reaction to the criticisms, Plege updated his paper on the RxIve on September 3, 2008, and again on August 9, 2009. So far, Plege's paper has not been published in a peer-reviewed journal. Drawing from research performed to assess the safety of the RHIC collisions, the LHC Safety Study Group, a group of independent scientists, performed a safety analysis of the LHC and released their findings in the 2003 report, Study of Potentially Dangerous Events During Heavy Ion Collisions at the LHC. The report concluded that there is no basis for any conceivable threat. Several of its arguments were based on the predicted evaporation of hypothetical microblack holes by Hawking radiation, which yet was not confirmed experimentally, and on the theoretical predictions of the Standard Model with regard to the outcome of events to be studied in the LHC. One argument raised against doomsday fears was that collisions at energies equivalent to and higher than those of the LHC have been happening in nature for billions of years, apparently without hazardous effects, as ultra-high energy cosmic rays impact Earth's atmosphere and other bodies in the universe. In 2007, CERN mandated a group of 5 particle physicists not involved in the LHC experiments, the LHC Safety Assessment Group, consisting of John Ellis, Gian Giudice, Michelangelo Mangano, and Urs Wiedemann of CERN, and Igor Tikachev of the Institute for Nuclear Research in Moscow, to monitor the latest concerns about the LHC collisions. On June 20, 2008, in light of new experimental data and theoretical understanding, the LSAG issued a report updating the 2003 Safety Review, in which they reaffirmed and extended its conclusions that LHC collisions present no danger and that there are no reasons for concern. The LSAG report was then reviewed by CERN's Scientific Policy Committee, a group of external scientists that advises CERN's governing body, its council. The report was reviewed and endorsed by a panel of 5 independent scientists: Peter Braun-Munzinger, Matteo Cavalli, Sforza, Gerard Tuft, Brian Weber, and Fabio Zwerner, and their conclusions were unanimously approved by the full members of the SBC. On September 5, 2008, the LSAG's review of the safety of LHC collisions was published in the Journal of Physics G, Nuclear and Particle Physics by the United Kingdom Institute of Physics, which endorsed its conclusions in a press release that announced the publication. Following the July 2008 release of the LSAG Safety Report, the Executive Committee of the Division of Particles and Fields of the American Physical Society, the world's second-largest organization of physicists, issued a statement approving the LSAG's conclusions, and noting that this report explains why there is nothing to fear from particles created at the LHC. On August 22, 2008, a group of German quantum physicists, the Committee for Elementary Particle Physics, published an open letter further dismissing concerns about the LHC experiments and carrying assurances that they are safe based on the LSAG Safety Review. On June 18, 2008, Stephen Giddings and Michelangelo Mangano issued a research paper titled The Astrophysical Implications of Hypothetical Stable TV-Scale Black Holes, where they develop arguments to exclude any risk of dangerous black hole production at the LHC. On August 27, 2008, this safety review was published in the Physical Review D, and a commentary article, which appeared the same day in the journal Physics, endorsed Giddings and Mangano's conclusions. The LSOG report draws heavily on this research. On February 26, 2009, a paper titled Exclusion of Black Hole Disaster Scenarios at the LHC was published in the journal Physics Letters B. The article, which summarizes proofs aimed at ruling out any possible black hole disaster at the LHC, relies on a number of new safety arguments, as well as certain arguments already present in Giddings's and Mangano's paper, Astrophysical Implications of Hypothetical Stable TV-Scale Black Holes. On March 24, 2008, a complaint requesting an injunction to halt the LHC's startup was filed by Walter L. Wagner and Luis Sancho against CERN and its American collaborators, the United States Department of Energy, the National Science Foundation, and the Fermi National Accelerator Laboratory, before the United States District Court for the District of Hawaii. The plaintiffs demanded an injunction against the LHC's activation for 18 months after issuance of the LHC Safety Assessment Group's most recent safety documentation, and a permanent injunction until the LHC can be demonstrated to be reasonably safe within industry standards. The United States Federal Court scheduled trial to begin June 2009. The LSAG review, issued on June 20, 2008, after outside review, found no basis for any concerns about the consequences of new particles or forms of matter that could possibly be produced by the LHC. The United States government, in response, called for summary dismissal of the suit against the government defendants as untimely due to the expiration of a 6-year statute of limitations, since funding began by 1999 and has essentially been completed already, and also called the hazards claimed by the plaintiffs overly speculative and not credible. The Hawaii District Court heard the government's motion to dismiss on September 26, 2008, and on September 26, the court issued an order granting the motion to dismiss on the grounds that it had no jurisdiction over the LHC project. A subsequent appeal by the plaintiffs was dismissed by the court on August 24, 2010. On August 26, 2008, a group of European citizens, led by German biochemist Otto Rüssler, filed a suit against CERN in the European Court of Human Rights in Strasbourg. The suit, which was summarily rejected on the same day, alleged that the Large Hadron Collider posed grave risks for the safety of the member states of the European Union and their citizens. Late in 2009, a review of the legal situation by Eric Johnson, a lawyer, was published in the Tennessee Law Review. In this paper, Johnson stated that, given such a state, it is not clear that any particle physics testimony should be allowed in the courtroom, in reference to the dual problems that, the scientific arguments regarding the risks are so complex that only persons who have devoted many years to particle physics study are competent to understand them, but b, any such persons, by reason of this huge personal investment, will inevitably be highly biased in favor of the experiments, and also endangered by severe professional censure if they threaten their continuation. In February 2010, a summary of Johnson's article appeared as an opinion piece in New Scientist. In February 2010, the German Constitutional Court rejected an injunction petition to halt the LHC's operation as unfounded, without hearing the case, stating that the opponents had failed to produce plausible evidence for their theories. A subsequent petition was rejected by the Administrative Court of Cologne in January 2011. An appeal against the latter ruling was rejected by the Higher Administrative Court of North Rhine-Westphalia in October 2012. Today, the Large Hadron Collider continues to operate safely, having successfully completed multiple experimental runs and produced groundbreaking scientific discoveries. The fears that once dominated headlines in courtrooms have been thoroughly addressed through rigorous scientific analysis and years of safe operation. The LHC stands as humanity's most powerful tool for probing the fundamental nature of reality, pushing the boundaries of our understanding of the universe while maintaining the highest safety standards. As physicists continue to analyze the vast amounts of data generated by the collider, we can expect new discoveries that will further our knowledge of particle physics and the cosmos. The successful operation of the LHC demonstrates not only the power of international scientific collaboration, but also the importance of evidence-based decision-making in addressing public concerns about cutting-edge technology.